All right, so the first thing you want to do, remember with these, is we want to write it each term, or each term on top, as its own term of a polynomial. So like I'm going to take the 3x squared over x squared, well that just equals 3, minus 5x over x squared, that's going to be 5 over x, and then plus the 1 over x squared, there's no way to simplify that, so that's just 1 over x squared. And then we can go ahead and find the derivative. And for each of these, we can do that just using power rule, because remember that this is going to be the same as 5x to the negative 1 and x to the negative 2. And so that's what we're really doing the derivative of. And so now I can do the derivative. The derivative of 3, of course, equals 0. That's gone. But then I do the derivative of negative 5x to the negative 1. So I do the negative 5 times negative 1, which gives me a positive 5. And then I subtract 1 from the exponent, so that's going to give me 5x to the negative 2. Then, for the next one, we multiply by the negative 2, our exponent, so it becomes minus 2, x to the negative 3. And then we can go ahead and turn it back into our fractions here, so that's going to be 5 over x squared minus 2 over x cubed. But in this case, we're not done. So in order to now get this answer as a single fraction, we have to combine some like terms here. Well, in order to do that, we have to have a common denominator. So I'm going to turn that into 5x over x cubed minus 2 over x cubed. And so then when I go and make it just a single fraction, we're going to have 5x minus 2 over x cubed. And so then that will be our final answer.
That's good.
So now that we did this problem, the thing is though that we really had to go through a lot of steps, right? And if we could just go straight from our original fraction down to that answer without having to go through all of those steps of turning them into negative exponents, each in their own individual term, it'd be a lot easier. Plus, what if it wasn't just over x squared? What if it was something more complex? We'd need a way to deal with that. And so today we actually are learning a new rule. Remember, you have the product rule? Well, on the same sheet, right below product rule, we're going to be able to add the quotient rule. So add the quotient rule to your derivative rules now. You know, as you take a look at this though too, you're going to have to actually be looking ahead towards memorizing it too. Because you're going to have to be able to use the quotient rule just like you use the product rule. So anytime you see something that's set up for use in quotient rule, you're going to have to be able to pull this out of the air. You're going to have to be able to pull this out of your mind and know that this is what it looks like. And so a way to help memorize this and a way to help remember this formula is this. Low D high minus high D low over the square of what's below.
Yeah.
Add this to your notes on this and that will help you to remember it. And so you'll notice kind of where this idea comes from. Low is a reference to whatever function is on the bottom. D high, the derivative of whatever is on the top. So D high. So then over here, high is the function that's on the top, and D low represents the derivative of the bottom function. And then the square of what's below, because notice we take whatever the bottom function is, the g of x here, and we square it to put it on the bottom. Now, for a lot of you I know, looking at this with the d over dx notation, it's tough. But we do have to get used to it, so yes, I do need you to have this form in your notes. But you might prefer maybe some prime notation as well. So I'm going to give you what this same formula would look like if we wrote it with prime notation. If you also want to have this added into your notes, you can. But of course it means the same thing. All right, so now that we've gotten down quotient rule, we can see what the general formula is. Next up is seeing how do we actually apply it, how do we use it. And so for that, I'm going to go back to that same function that we found the derivative of at the start of class today. Just we're going to find the derivative of this one using the quotient rule. So again, write down the function. So now to plug this into quotient rule, when we use quotient rule, we're actually finding the derivative. So we go straight to the f prime of x here. We don't have to change the form in any way. And so we do low d high, which means the bottom function, which is x squared, times d high, which is derivative of the top function. So the derivative of the top, that is the derivative of the numerator, derivative of 3x squared is going to be 6x. Derivative of the 5x is just 5, and the derivative of 1 is 0, so that goes away. Then it's going to be minus high d low. So the top function gets left alone in this case. And then that gets multiplied by the derivative of the bottom, d low. Derivative of x squared is 2x. And then that's all over the square of what's below. So that's going to be taking the x squared and squaring it.
Okay.
Now you notice at this point, all I've done is just plug this stuff into the quotient rule. I haven't done any of the work on it yet. I haven't simplified anything yet. All I've done is plug in. Please note that when you plug in, having these parentheses is going to be especially useful, because you notice we're subtracting these. And if you leave off the parentheses, as I know a few people are prone to do, it's going to cause you some major trouble down the line. Okay? So, having gotten to this point, everything else we do is going to be simplification. Technically, this is the derivative function. Just, I want to go ahead and simplify this one. So, first up, let's go ahead and distribute the x squared in, and we'll distribute this 2x into there as well. Now, when you do that distribution, notice, again, since I'm subtracting, I keep the parentheses around that second part. If you lose those parentheses, all of a sudden everything goes sideways on you, right? And so keep track of those parentheses until you actually get to combining the like terms on the top, which is going to be our next step at this point. And so when I then go ahead and combine the like terms there, doing that subtraction, the whole thing works out to be 5x squared minus 2x all over x to the fourth, which notice can simplify because every term has an x in it. And so I can go ahead and pull an x out of every single term, leaving me with 5x minus 2 all over x cubed, which, as you'll remember, is the exact same answer we found when we did it the long way before, the other way where we actually had to turn every single term into its own term and then use power rule. Now some of you are looking at this process and you're thinking, this actually seemed a lot harder than doing it the other way. And you then would be wondering, okay, why do we need this? Here's 7 different functions. For some of these, you could have done before. You could have found these derivatives without having to use quotient rule. You could have just done it like we did that first problem, where you turned each term into its own thing. Others, no, you're going to need quotient rule for it. And so, take a look at each one of these. Think about which ones could you do without quotient rule, and which ones do you have to have quotient rule for. And so, for instance, if I took a look at f of x there, I can turn that into a couple different terms. I can make it into x over x squared plus 1 plus 1 over x squared plus 1. But can I find the derivative of each of those? No. We can't do that. I mean, if you're going to find the derivative of those, you'd still need to use quotient rule, but now you'd be using it twice. That doesn't sound like a lot of fun. So you'd actually have to use quotient rule on this one in order to be able to find its derivative. The other methods that we've learned simply would not work. Okay, g of x. Do we have to use quotient rule for that one?
No.
No. You actually could do that by turning it into x over 5x squared and 1 over 5x squared. And just using a power rule there, that would work. Can you use quotient rule? Yes. What about h of x?
No.
Do we have to use quotient rule? No. You could do it the other way as well there. What about j of x?
Yes.
It looks like we got to use quotient rule here, yes. Okay. K of x. Do we need it for k of x? Yeah, looks like we do. Okay. What about m of x? Yes. You will need quotient rule there. Last one, n of x. Do you need it there? Do you need to use quotient rule on n of x? No. Which for some of you is all of a sudden, oh, wait, that doesn't follow the pattern. But if I looked at how else could I rewrite it, well, x squared minus 1 factors, doesn't it? In fact, that would be x plus 1 times x minus 1 all over x plus 1. Notice those x plus 1s would cancel out. That whole thing actually just equals x minus 1. So yes, you could do that without quotient rule. The derivative would equal 1. But again, can you use quotient rule? Yeah. And so there's multiple methods now that you have at your disposal, and part of what you're going to be doing on a lot of problems is actually starting out by deciding which method am I going to be using on them. Good point. Yeah, m of x. That one factors down too, doesn't it? And in fact, if we factored m of x, that bottom would become x times x minus 1. The x minus 1s would cancel out, so the whole thing actually equals just 1 over x. No quotient rule needed. Excellent. Now, one of those that we had to use the quotient rule for was f of x. So to practice on one that requires that we have to use quotient rule, please go ahead and find this derivative. Now, when you just plug into difference quotient, this is what you'd be looking at. You might be wondering, do I have to write the 1 there? No, you don't strictly have to, but by putting it in there, we remember that we actually took the derivative of the top there. And then from here, the only things we'd have left to do is just any simplifying. Although this one didn't actually say that we had to simplify it, so technically we could be done at this point.
Okay.
And so we could multiply it all out, but still, it cleans up to this, which is a little bit better, but still not totally there. But this goes ahead and shows us, kind of where we can take it and what we can do with these. But we found the derivative much more easily this way, right? And in fact, we couldn't have found the derivative without the quotient rule for this. I want to try one more. Go ahead and find this derivative. But again, you won't even have to simplify it. Go ahead and just find the derivative, but you don't have to simplify this time.